problem that is not the one that you intended. This is even a bigger problem because actually there is no algorithm that directly solves the problem. Most systems nowadays learn from data. And when they learn from data, they try to optimize some function. And that, of course, naturally, is the evaluation metric. So you can, if you choose the wrong metric, you can even be building the wrong system. I also have to say it's very important to have a good metric because science is about making small improvements. And of course, there are counterexamples. No? If you are Page and Brain and you build Google, you do not need any evaluation metric. You have the metric effect. No, you don't need to evaluate. Probably some of you already know about this story that it's well known in the information retrieval community that Page and Brain, when they built Google, they submit a paper to CIR and it was rejected. For many reasons. One primary reason is that there was no evaluation. Okay, when you do Google, you really don't need evaluation. But you have to, and probably you are all thinking of building the next Google. But bad news is very unlikely that you will do that. In information retrieval, the equivalent of building Google is like a scientific revolution in physics. It's like inventing quantum mechanics or inventing the theory of gravity. That's something that happens very, very rarely. And it completely changes the landscape. For all the rest of the 99.9% of the research, it's all about putting yourself on the shoulders of giants, which means making small improvements on things that have been previously studied. And that's another reason to care about the metrics that you're using for your problem. So these are the problems that we are going to study in the next two sessions. I will be talking about filtering and clustering, and Enrique will be talking about retrieval. And this is just the structure of the problem. So you have, in the case of filtering is like spam filtering. There is an incoming set of documents, and there are some documents you want to retain and some documents that you want to discard. Okay? And then you have a gold standard, which is a set of manual assessments that tell you what is really relevant and what is really something you have to discard. And then the system output is supposed to be exactly of the same shape. So the system output is a set of documents that the system say they are relevant, and a set of documents the system say they are relevant, they can be discarded. Okay? I have put it in this way just to highlight the fact that this is like binary classification, that there is a nuance, that this binary classification, that there is one class that has a priority, one class we want, and one class that we do not want. Okay? So an evaluation metric has to compare the system output with the gold standard. Somehow, as Stefan explained, has to tell us how similar the output of the system is with respect to what we know is the ground truth. If you look at the retrieval system, the gold standard, at least in the classical definition of document retrieval, is exactly the same. So you have a set of documents manually judged as relevant, and you assume that everything else is irrelevant. You may have a number of degrees of relevance, but basically this is it. However, note that the system output does not have this shape. The system output is a rank of documents. Note that when we try to study this problem, it's tricky to talk about similarity, because you talk about similarity between two structures that are not of the same form. So it's trickier. And in fact, well, I forgot to say you can do as many questions as you do. But if you don't, I will make questions also. And my first question is, so for retrieval, the gold standard is just a set of binary assessments, which is exactly the same as for filtering. So why don't we apply evaluation measures that we use for filtering? Or why we take these two problems as different? Why there are two fields of the study which are very different? Any answer? The one that gets the right answer can go to the beach right now. We will see more about this later, but the substantial difference is that there is an almost infinite, in practical terms, amount of irrelevant information. There is just a very, very, very tiny fraction of the document collection that is relevant. And that completely changes the way we can approximate the problem and also evaluate the problem. And finally, there is the clustering problem. In this case, we are not discarding anything. We are just saying that certain sets of documents are related somehow. And as in the filtering problem, the gold standard, the assessments by humans, and what the system provides has exactly the same structure, just groups of documents. Okay? Yes, these are 3 problems, and only one is called retrieval, but as you work on real life problems, you will find out that these problems, these techniques naturally merge. I'm just going to give an example, which is web search with diversity. You can think about the web search with diversity problem in this way. Think of the query camel. As Martin explained before, a first diversity aspect is that the query is ambiguous and there is only one intent. Camel can mean many things. And so you have to solve this ambiguity first, which you can look at as a filtering problem, in which you will probably need some more information from the user. So you can have the van, the animal, the cigarette, etc. Once you find out which is the meaning that the user intends, you still have another level of diversity, as Martin explained, which is this of subtopics. So you may want a search engine to tell you, okay, so about the camel rock band that you are interested in, we have documents about their history, we have places where to listen to the music, you have lyrics, you have opinions about the music, you have sheet music. These are different subtopics, and the user may be interested in more than one of them. And a good way of presenting the information in the right way to him is solving both problems. So you have clustering, you have filtering, and you have search, and you have ranking. You have everything inside. So it's interesting to look at all these problems, even from the narrow perspective of doing information retrieval. So these are our 3 problems: input, output, and we want to compare them to assess the quality of the system. And as Stefano has explained, when you go to the pharmacy and ask for a thermometer, you are getting a huge range of possibilities. You are not quite sure if they measure the same or they do completely different stuff, and you don't know what to do about it. Yeah, this is more the situation. Probably you have all experienced it. So what do we do? Well, I'm going to summarize for you the state of the art in picking up a metric. There are basically 4 strategies. The most popular strategy is choosing the most popular metric, which is reasonable. It's not completely crazy, because if you have to compare yourself with previous state of the art, you need to use the same metrics. So you are somehow conditioned by previous research. You can't just decide on your own what is the right metric for a problem. Of course, this has a potential problem, is that someone made the wrong decision at first. A measure anyway becomes a standard because people use it. And people use it because it's a standard. And it's a vicious circle, and it's very difficult to escape from there. In fact, if you are trying to solve a new problem, please be very careful. I tell you by experience, I wasn't very careful. Because you choose a measure, and then you enter this problem. I call this the Hilton Chihuahua metric effect. Because this is something that happened with Paris Hilton in California. She bought a Chihuahua, and suddenly California was flooded with Chihuahuas, which is total catastrophe. Well, that's what you can provoke. And I will give you, unfortunately, some examples with my own research later. There is another strategy, which is quite popular, which is getting creative. What do I do? Do I read 100 papers about 100 metrics to find out which is the most suitable? Or do I invent something new and publish a paper about the new metric? It's tempting, huh? If, for instance, in machine translation, this happens all the time. They have hundreds of metrics and you don't even know what are the differences. In fact, I think they publish more papers with graphs like this in which every point is a metric instead of a system. This graph is from one of our papers, by the way, so I'm not blaming anyone. There is another strategy which is also popular, which is use the simplest, which is, again, is not a silly strategy, because maybe out of 100 metrics, you don't really know what 80% of them are saying. So even if you have a metric which is not perfect, if you understand what it is saying, at least you won't make wrong assumptions about it. So it's not so stupid. This is particularly a valuable strategy when you have clients. When you are in a company developing a product and you want to tell them how good is your product, you better use a metric that they understand. Otherwise, they won't trust that this is the metric which is really accepted in the scholar community. The scholar community, come on. And finally, this strategy is not popular. No one has ever used it. I just include it for completeness, which is, okay, I have 100 metrics, I try them all, and this is the one that says that my system is better. But as I say, this is just theoretical. No one has ever tried it. So this is basically it. That's the state of the art. And we want to do more. And in the presentations by Enrique and myself, we are going to study these three problems from the point of view of axioms or formal constraints. However, our point of view, so it's the same methodology Stefano has presented, but used in a very different way. Because Stefano is more like a biologist. No? He sees all this wonderful range of metrics and he tries to find out what are the things they have in common, and he describes the world of metrics. Our talks are more like the hunters. We want to kill them all and maybe just fortunately keep one to use it and forget about all the rest. So that's what we are going to do, and that's why we are going to save you reading many papers. The idea is very simple, and I'm going to repeat it just to make sure that you are focused on our way of doing things. And you can think that it comes from physics also. So sometimes when you model a problem in physics and you try to give a formula that explains the phenomenon, you don't know exactly what to do, but you can start by stating constraints. Very simple things that any function that models a problem must satisfy. In this case, if you are trying to model the vibrations of a string, you know that at the beginning and at the end of the string, the function will always be zero at any point in time. So that's extremely simple. Physicists go a long way with this kind of constraints. And maybe we can do the same with our evaluation metric. So no idea what the shape of the evaluation metric is, that it must satisfy this very simple constraint, intuitive constraint. And this is what we're going to do. We're going to make all our constraints in a very particular way. So Stefano has shown a range of possibilities for stating axioms. We're going to fix on one way of action, which is we compare the output of two systems. So the test collection is fixed, the queries are fixed, the assessments are fixed, and we just compare two different system outputs. And then we say, any suitable evaluation metric must say that this distribution is better than this one. Okay? And you will see we can go quite a long way with that. So that's about motivation. And in my talk, I will study the clustering and the filtering problems. I'm going to study with the clustering problem for, let's say, historical reasons. It was the first one we attempted. And, well, I have to say, I'm trying to convince you to really care about the metric before starting with the problem. But of course, I didn't do that in the past. And then first I'm going to tell you about some catastrophic failure that we had. As Theodora has said, we have run a number of evaluation campaigns on different information retrieval related tasks. And one of them was where people search. We called where people search to the problem of typing in a person's name in a search engine and seeing what comes out. When you type in a person's name in Google, you get a list of results. That person names are very ambiguous in very different degrees. So it's as likely to have 100 results about the same person that having 100 persons in 100 results. We have been doing test collections about that, and it's equally likely. So it's amazing the variability that you have there. If you are interested in one particular person, for instance, when we type John Tate, probably we are all interested in the IR researcher. We would like the system to cluster results according to the different people sharing this name, so that we can quickly focus on the person that we are interested in. So here we want the system to recognize that all these documents are about this person, the IR researcher, and all these other documents about this American football player. Okay, so that's a clustering problem, and we ran 3 evaluation campaigns on this problem. How did we choose our metric? We went for the popular metric approach, and we choose the purity and inverse purity metric pair, which works as follows. So you have classes, let's call classes to the manual assessments. Okay, so the assessor saying, so all these documents are about one person, which is an IR researcher. So you have clusters, which is the system output, and you have classes, which are the clusters, the true clusters. Purity looks at clusters, and looks if a cluster is clean. So if a cluster mostly contains things that are, in this case, referring to the same person, then it's a pure cluster. Okay? And inverse purity focuses on classes. For every class, it looks at the cluster that contains most elements from this class. So it looks whether a class is grouped into a single cluster. Okay? So you can decide on the quality of the system by combining these two things. So what you have to do, you have to compute purity and inverse purity for each test case. Then you have to combine them into a single quality measure. And here we did it with a harmonic mean of purity and inverse purity, and I will talk a little bit about means at the end of the talk. And then you have to average of the test cases. Okay, that's what we did. And this is what happened. So we had 2 baselines. Let's call them bottom lines better, because they are not real baselines, which is a baseline that does not group anything. So for every document makes a cluster. So nothing is grouped. Okay? And the opposite baseline, which is I just make one cluster with everything. So here I am assuming that every document is about someone else, and here I am assuming that everything is about the same person. Okay? So let's see what happens with our evaluation metrics. In this case, all clusters are pure, because in any cluster you only have members of one class. So purity is 1 for every cluster. So you have perfect purity here, and inverse purity is not so good, of course, because you don't get a good coverage of any class except for the ones that have one member. What about the other baseline? When you look at how well you put everything from one class together, you always find one cluster that has everything from that class, because you have everything together. So inverse purity is perfect, and then purity is not so good, of course. Okay? So we had a participant that came up with a cheat system. He didn't submit it, he just told us about it. He said, there's something wrong with this metric, because what if I give this result? And this result is adding up the 2 baselines. You can do this in our problem because you can put one document in more than one cluster. For instance, you can have a book result page from Amazon, and you can have more than one John Tate that has wrote a book. So this page is relevant for more than one John Tate. So you want to put this item in more than one document. And so he exploited that fact to give this result. So he delivers one cluster per item, and then one cluster with all the items repeated inside. How good is this solution? Well, we know it's crap, it's useless. It's not a baseline. It's not even a dumb baseline. It's something that you know it's not going to serve any purpose to anyone. But purity is not that bad, because you have a lot of clusters that are of perfect purity. And what about inverse purity? Again, for any class you are interested in, you find all the documents in one cluster. So inverse purity is perfect. And this was the result. If you put this cheating system, which again, I repeat, it's not a baseline, into the results of the competition, you find out that that completely useless system could be scored second in the campaign. So we discovered that we had a problem. We discovered there's something called evaluation metric that you really should take care of before embarking on this kind of stuff. And so we started over. Yes.
Why do you say this is not a baseline? Because normally, in many efforts, I know the ones in classification, etc., people always consider, the cheat system as a baseline. Okay, so the majority class classifier is the baseline you need to overcome.
I guess it's just a label. For me, well, when you write a paper, a baseline is the best system available out there, and you try to improve on that. That's why I call my baselines bottom lines. But also, a baseline is something that, even if it's very gamma, like our baselines that do not think, do not look at the data, they just simply do the same thing with any data that comes out. They can provide some valuable information. For instance, if it turns out that the data collection is very scattered and there is very little to actually cluster, maybe the baseline of not clustering anything at least doesn't harm you a lot. But this is a cheating system and not a baseline, because it cannot provide any useful information. It's just misleading. It's repeating everything and you don't see anything you don't see any information there. But it's just a label for me. Okay. And also a cheating system is something that you devise with the purpose of optimizing the metric, knowing that you are not providing any useful information. That's what I mean by cheating. As I said, he didn't submit such a system. He just pointed out that we had that problem.
Okay, so I have a second part. Actually, the problem is that when you have a learning, especially supervised learning, and you optimize a given metric, say the harmonic mean between purity and inverse purity, you might find out that your learning algorithm discovers the cheat system because...
Exactly. That's what I said at the beginning. That's why it's so important to choose the right metric, because any system nowadays is doing some learning. So it's out in the wild doing his own stuff, and he can end up doing this kind of stuff. So that exactly exemplifies what I said before. So this is again our face when we discovered that. So we started thinking for a change. And we started thinking about establishing these formal constraints, as I said before. And here you have the first example of a formal constraint for this problem. So let's assume this is a system output, okay? And we are interested in this. So black is a class, white is a class. And the system is putting all this information together, okay? Now imagine a system that does exactly the same with all other data, but in this case, with this, it's splitting correctly the black class in one cluster and the white class in one cluster. So this is a way of saying that the quality, so the evaluation metric applied in this system, must give a higher value than to this system. Okay. How many people agree with this? No. How many people disagree with this constraint? I'm trying to not to be biased by people sleeping. No one disagrees, of course. Great. I don't really care about what you disagree or not, but it's good to know. Okay. What about purity and inverse purity? Well, I mean, I don't care because we have already published it and we already tested it with users. And it's not really that I don't care. So purity and inverse purity. We say we were doing the harmonic mean of that. Would that metric satisfy this constraint? Well, inverse purity. Whatever was grouped, how classes were grouped before, here, they are equally grouped here. So inverse purity is going to be the same. And obviously, there is a gain in purity here because these two clusters are purer than this one. So in any way we combine these two metrics, with any mean that we use, the arithmetic, the harmonic, or whatever, or the geometric, we are going to satisfy this restriction. You are probably thinking, any metric that people devise will satisfy this restriction. Wait a little bit. Well, let's look at this second constraint, which we call cluster completeness. It's like the complementary to that. So if we have two clusters which contain information about just one class, and we put them together, then the quality of this system output has to be better than this one. If a metric does not satisfy this for any example of the data, then it's not a perfect metric. Okay? Anyone disagrees with this? Okay.
Well, technically you're not wrong, are you, if you do that?
Okay. What about purity and inverse purity, which at that time when we did this study, I believe they were the most popular metrics. Do they satisfy this constraint? Fabrizio, what do you think?
I think that if you have a situation in which purity is 0, then the harmonic mean doesn't satisfy this, because you have a strict...
Well, that's the problem of the harmonic mean. I don't want to get into that problem now, but later, but think of the following. Purity of these two clusters is 1. Purity of this cluster is 1. But what about inverse purity? So about the black class. Inverse purity is going to look for the cluster that has the largest number of elements from that class. It doesn't have to be this one. There can be another cluster with 20 black elements. So inverse purity may not care about this. And purity is the same because everything is pure in both sides. The things that are different. So purity and inverse purity do not have to hold this constraint in every situation. So these are the most popular metrics. This is an extremely basic constraint, and we already found that it's not satisfied by this couple of metrics. Okay, we have overall 4 constraints. Let me give you the other 2. This constraint that we call Radbach is about what you do with noise. So here you have a cluster that contains things from one class, and then one thing that is misgrouped or misclassified with it. And then you have another cluster which contains a variety of things. Okay, so you see here that everything is from a different class. What we propose as constraint is that if we remove this noisy item and put it together with a lot of noisy items, that distribution intuitively is better than this one. Anyone disagrees with this? I know that for some of you this is not so trivial, right? This comes from the fact that when you look at a web search that includes clustering or a directory, web directories such as daemons, you have some things that you can cluster and then you have the other stuff. And so naturally for a user, this situation is easier to handle than this one, okay? And finally, we have a last constraint that says the following. Here you have classes made up of 2 elements, and they are put isolated in single clusters. Okay, you have this and this and this and this and this. And then you have one large class with all elements from one class. And what we say is that if you put all these classes together correctly, I'm skipping you the mathematical notation or the details because it really doesn't add to the discussion, and you miss this one, this distribution should have a higher score than this one. Again, from a user's perspective, it's natural to think of this. Anyone disagrees?
I don't disagree, but I'm just wondering to what limit. So if on the right-hand side, it still made the same mistakes except for one, but those groups are paired up to one of them.
To be honest, I don't remember the exact formulation because this is from 2009, but there was an explicit, so the number is fixed. So here is something like you have the same amount of items here than in here, something like that. So there is a precise mathematical formulation so that we can make formal proofs on that. Okay?
Yeah, okay, so your example could change.
Yeah. So, yes?
Let's say I wouldn't be able to say whether I agree or disagree. This axiom actually strikes me as weird, okay, because it seems a complex combination of conditions, okay, while I would intuitively think of axioms as specifying a very primitive condition.
Mm-hmm. Well, I think that the first two axioms are very primitive conditions.
Right.
But as I said at the beginning, we are hunters, not biologists. And this last constraint is specified precisely to discard some, to kill some metrics. The thing is, does it make sense or not? So what we did, instead of asking people like I'm asking to you now with abstract bullets, we did a test collection in which we showed users actual distributions of actual news documents, and we asked them which of the two distributions you like more. Okay? So we ran that experiment, and this is what we got. Do other humans agree on our constraints? When they see examples and they say, this one is better, or this one is better, or this one is better, we ran this for a number of times at different situations, with different collection sets and with different people, and this is the level of agreement that we got. This is really what I mean that I don't care about what you say, because it's probably, the intuition comes up when you see actual data. And the intuition, so for the first two, that you all agree they are correct, you have 92 and 90% agreement. And for the other two that could seem weirder in abstract terms, when you put data in front of people, the level of agreement is even better. And for the last is 100%. That's something you never see. You know, these are humans. I think 92% of agreement is if you ask in the United States whether Elvis Presley is dead. 92% of the people agree that he's probably dead. Okay, so you can get anything better than that. In fact, I have here one example, just to tell you as PhD students how weird humans are. So we are computer scientists, we cannot understand humans. Well, in fact, I am a physicist, so I'm in the middle ground. I cannot understand humans, but I cannot understand computer scientists. It's a nice situation. Okay.
You understand yourself?
Sometimes. Let me make a very small test with you. If anyone knows anything about psychology, has probably seen this before. So there is this language in an isolated imaginary tribe somewhere in a forest that has two words for these two different shapes. One of the words is booba, and the other one is kiki. So now I ask you, figure out which one is booba. So, how many people think that this one from the left is called booba? Fantastic. And how many people think it's kiki? Kiki. 3. Fantastic. I think this is the time that there has been more people listening to this, because I never had these counterexamples. These 3, these are the ones that I'm going to invent the next video. Anyway, it's absolutely striking to me that 95% of you agree that this is called booba. Why? Okay, there's some synesthesia. You associate instinctively the shapes with the sounds. But why are you so confident? I just can't understand it. It's amazing. So for this thing, which there's absolutely no rationale behind it, everyone agrees what is booba and what is kiki. But when you ask people, is this document relevant to this query? You never get anything better than 65%.
They run this experiment in Arabic countries, you know, where they read the left to right.
Oh, interesting.
So right, left, you know, that's
Why I'm telling you this? Just to tell you how strange humans are. And now I'm including you as computer scientists because I ran the experiment on you. every time you get human in the loop, you get into trouble. You probably, Diane, will have good examples later this week.
I guess it has been tried in different cultures.
I think so. In any case, we have these 4 constraints, and then we analyze metrics. First, we see that there are metric families for which you can do a formal analysis at once of all of them. So here we have the 4 constraints, and here you have the metric families. So about purity and inverse-purity, which belong to a set of metrics based on set matching. As we have seen, just with the second, it fails to complain with. And also the rack-back constraint, this family doesn't satisfy that. So you can skip reading a bunch of papers here. What about metrics based on counting pairs? What means counting pairs? They look at pairs of documents. What can happen with a pair of documents? They can belong to the same class and be in the same cluster, which is fine. They can belong to a different class and be in a different cluster, which is also fine. And you can do a growing association, no? Say that in the same class but different cluster or the reciprocal. So you can take all possible document pairs and you can do all kinds of combinations with these 2 figures to get different evaluation metrics. Maybe the simplest is this one. The random statistic is just the things you have, the pairs you have grouped correctly or not grouped correctly, divided by the total number of pairs that you have. Okay? It's like a kind of accuracy. How many pairs did you get right? That's fine. And that's why we devised this constraint to exclude this kind of metrics. Because the number of pairs grows quadratically with the number of items. And what happens is that, you remember that constraint that we say, removing one document from a large set is not so bad as splitting a large number of very small sets. Now, of course, if you are counting pairs, that is not the case, because when you remove this one, you are destroying at least 4 pairs in this example. Okay? And here you have 4 clusters of size 2, so you are doing exactly the same. You are destroying 4 pairs. So you cannot distinguish this. You cannot satisfy this constraint. So yes, we devised this constraint because we saw that problem in that family of metrics. So you can skip another bunch of papers. Metrics based on entropy, I'm going to skip the definition here. But, yeah, I'm going to skip it because we are very late today. But, well, just trust me, you don't even have to read them. They fail to satisfy one of the constraints. Metrics based on editing distance, which see how many steps do you have to take from the system output to the gold standard so that they are the same. So the more steps, the worse is the distribution. And also they fail to satisfy this constraint. And then there are the B-cube metrics, which are versions of precision and recall that come from the information extraction community. It was a pair of metrics that initially was only used within that community. And luckily for us, this is the only metric or metric pair that satisfies every constraint. And I say luckily because you can't get any better than that. Looking at dozens of metrics and discarding all of them except one. That's just fantastic. So, you only have to care about how this metric works, and you can forget about anything else. How B-cube precision and recall work? Well, I talk at first purity and inverse purity focus on clusters and classes, on the sets. B-cube metrics, instead, they focus on elements. So they focus on one element, and B-cube precision is how correctly is related to the items which are in the same cluster. Okay, so in this case, this element is correctly related to these 3 elements and with himself. It's something tricky in the measure is that it counts himself also to avoid zeros and things like that. And incorrectly related to 1. So the precision in this case is 4/5. B-cube recall takes the same element and looks at the other elements in his class. And in this case, it's correctly related to this 4 and is incorrectly separated from this. Okay, so recall is 4/6. Basically, that's how PQ precision and recall work. Then you have to average over elements, etc., and you get the evaluation method. So this is the outcome of a pure formal analysis. Is it of any practical use? When we started with the problem, when we came back to the results of our system, of the systems in the competition, ranked with BQ, precision and recall, the cheat system goes straight to the bottom, which is like a great result, because it shows that the formal study of metrics pays off in practical terms.
This was the cheat system optimized for the other measure.
Yes, right. Exactly. But any metric that satisfies these 4 constraints has some theoretical solidity, robustness, so to speak. Well, okay, this is the guy that was in trouble. It took me some time to find this picture, but he's happy now. Okay, so that's about the clustering. I have simplified, of course. You can look at the paper. I have the reference at the end. I have simplified the discussion, but the thing we learn is that a very simple formal strategy can give you a long way looking at metrics. Surprisingly, metrics do not comply with simple assumptions, even if they are metrics that have been well thought and used for years. Let's go now to the filtering problem. So, as I said at the beginning, the filtering problem consists simply of discarding some elements from an incoming stream of documents. So it's binary classification. I want this, I don't want that. And it's with priority, because there is just one class that is of interest, and the other one is not. Binary classification is about the simplest problem that we can specify here. So it must be simple to evaluate, right? Well, if you look at filtering tasks in Trek, you can see that for every task there is a different metric that they use. So that gives a hint that maybe it's not so trivial to evaluate binary classification. Even worse, if you look at the different metrics that are used in filtering papers, and you look at how well they correlate with each other, because it could be the case that they all say the same about the data, and then there is no matter which one you use. But look at this. This is a comparison of the F measure with accuracy. So every dot is a system output. And this is how F measure evaluates and how accuracy evaluates. There is a correlation, yes. You can see this triangular shape that obviously is very little compared to what we expect. For instance, for an accuracy of 1, you have all a range of possible F measures. So this is not the correlation that we expect. They are saying different things about the data. If you compare the F measure with the utility measure, I'm going to talk about them later. Again, you see that you have a good correlation here in this area. So if when they are both high, that here anything can happen. You see, you have a square, so any possible combination you find here. If you compare accuracy and utility, you have also a set like this. So there is some correlation, but certainly they don't say the same. And if you compare logistic average misclassification with the F measure, you have a total chaos here. They say very different things. So really, we should be very careful when choosing the metric, because it's going to tell us completely different things, probably. So, let me make just a quick look at the metrics, so that to give you a flavor of why there are problems and why it's not so easy. So, here you have the confusion matrix, so the system output, which is saying that something is positive or negative, and the gold standard that says something is positive or negative. Let me talk about true and false for the gold standard. And then it can be the case that they agree in that something is positive, true positives, or they agree true negatives. The system says negative, and okay, it's false. And then you can have different outputs in the other sides of the matrix. Okay. So, if you think about the classification problem, I think that almost instantly anyone would think of accuracy as the right metric to choose. So you have to make a number of decisions. For every document, you have to decide if it's positive or negative. Let's count how often I get the good result. Okay? So if I have, so I would sum the true positives and the true negatives. So all the cases in which I give the right answer, I divide by the total number of cases, and that's it. How can this be wrong? Looks like a perfect metric to me. The percentage of cases, I do it right. Well, there are many nuances and problems with that. The first one, of course, is that if you want to evaluate an algorithm rather than a system, an algorithm usually has a threshold. Anything, I get a number, anything above that threshold, I say it's positive, and below that threshold, I say it's negative. Many algorithms give a number, and then you have to put the threshold that you train on some training data or whatever. So some cases, if you want to evaluate the algorithm, you want to do it without specifying a threshold. One way of doing it is thinking about the true positive rate, which is out of the positive, how much I'm getting, and the false positive rate, out of the negative stuff, how much I'm getting. Okay? So if I get very strict at the beginning, let's see, yeah. If I am very strict and I don't get anything, both rates are 0. I'm not getting any good stuff, I'm not getting any junk. Then I put my threshold lower and lower and lower, and things start coming in. And I start getting good stuff and bad stuff, until eventually you get everything, and then both numbers are 1. So a good system could start here, going up here. So I take very little negative stuff, and I get a lot of positive stuff, and eventually get here. So the best system would draw like this square, and if we measure the area under the curve, this curve is called the received operating characteristic curve, and if we measure the R area under the curve, we can have an idea of how good the system is without setting thresholds. Okay, so that's one thing. But let's stick with system outputs. Okay, let's assume we fix a threshold and we have an actual result. What happens if the amount of negative and positive information in the ground truth is very unbalanced? What happens if there is very little valuable information? Then the false negative rate will always be extremely small, because there will be an ocean of negative documents out there. And accuracy will favor systems that say that nothing is positive. Systems that retrieve nothing and discard everything. So obviously, you cannot use accuracy. It's pointless, right? Can you think of a filtering case in which this is actually the case? And it's a very practical one.
Accepting document, except for when you review a paper, you just reject them all because they're one.
Well, I was thinking of retrieval. I was asking at the first, why retrieval is different from filtering? Do you remember at the beginning of the talk? And this is exactly why. Metrics that work for filtering do not work for IR, because it's a very, very degenerate case of filtering problem. And that's why IR researchers use a different shape of curve. Instead of focusing on the true positive rate and the false negative rate, they don't look at the negative, they just look at the positive. They still use the true positive rate, they call it recall, how much of the good stuff I'm getting, but they replace the other measure with precision. Out of what I get, how many are relevant. And then you have the precision recall curves you have also. Yeah, okay, fine, but each type of mistake may have a very different cost. So think of spam filtering, maybe removing something that is, for instance, the acceptance for a serial paper. It goes to spam, and you lose very valuable information. Okay, So the type of mistake has a different cost. Let me give you a real example from a Spanish telephone company. They see that all the time they are losing clients that go to other companies. And suddenly they realize that many of them, just before leaving the company, talk to someone from that is using another company. And so they start seeing signals that can help them predict who is about to leave the telephone company. Okay? And so what they want a filtering system, classification system that tells them who is about to leave. They want to call him and offer him a better offer, a better deal. They make a discount, and so they don't lose the client, right? In this case, there is a clear cost associated to each element in the confusion matrix. So what happens with the true positives? You keep the client revenue, and you lose a discount, right? You can measure that in actual money. True negatives, nothing happens. They are not going to change it, and you don't offer anything to them. False positives, okay, they were not going to leave the company, but you offer them a discount, so you lose this discount. And what happens with the false negatives? You lose them, so you lose the client revenue. All right, so in this case, for every item in the confusion matrix, you know exactly what you gain and what you lose. So what you want is what is called a utility measure. So you have each of the frequency you are in each of the elements in the confusion matrix weighted by these costs that we can compute, right? By the way, just an exercise that comes from a comment by Evangelos. Can we evaluate web search in terms of profit, which means clicks in sponsored links? So imagine that you work at Google and you see that the clicks on the sponsored links are getting high a lot, and you say, we are doing great.
Is that a rhetorical question?
If this happens, you have a problem because the quality of your organic results is getting low. That's why people click suddenly a lot on the sponsored link. So maybe you are making a lot of profit on the short term, and on the long term you may lose your clients because they go to better search engine. That was.
You've got two parties, right? You've got the users, and you've got, like, if they're clicking erroneously on sponsored links, they're unhappy, so they might go to things. And the people who are paying for the sponsored links,
which are happy, exactly.
Lots of people clicking on the links without buying anything, they go, well, I'm not going to offer as much money anymore, so I start making less profit from them as well.
Exactly. So sometimes you can establish things in terms of cost easily, like in the telephone company, but often you cannot. Now, what happens if the system ignores the input? And let me tell you that in my lab, we once built a SIGA submission reviewer, automatic. So you get a submission, you evaluate it, you give an answer, and we had 85% accuracy.
That would explain many things.
Of course, you all guess that the system is not looking at the submissions, it's rejecting everything. So great. 85% of the times, we did the same as the reviewers. That can be a big problem, depending on for instance, in this case, if you want to build a SIGA reviewer, the fact that you get 85% accuracy means absolutely nothing. The system is not helping you at all in solving the problem, even if it gets the right answer most of the times. So sometimes you need a metric that tells you how much information your system is providing. This system is not looking at the data, so it's not providing any information, right?
So, Julio, does that mean we could potentially start classifying reviewers or evaluating how good a reviewer is in terms of, because if like I said, I just reject everything, right? Cause it's just,
we have to do that. That's a great idea. Absolutely, that's what I meant. That's excellent. We have to do it.
yeah.
Informative reviewers. That's great.
I have a metric for that.
Okay, so there are a family of metrics for filtering, that look precisely at the amount of information that the system is providing. Here's an example, which is mutual information, and you have many factors that you add up of this form. And S and G is system and gold standard, and you can have, for instance, the system saying that something is, an item being true, and the system saying it's positive. So this is, what is the probability, the joint probability that an item is classified as positive and it's true, right? And then you have this shape. You have this joint probability, and here the independent probabilities that an item is true and that an item is classified as positive. What happens if the system ignores the input and does not provide any information because it says the same regardless of the input? In that case, the joint probability is equal to the independent probabilities because there is no conditional probability, there is no association. And then this formula comes logarithms 1. So this formula is 0. And that's the way this kind of formulas penalize non-informative behavior. So even if you are getting 85% of the data right, if you are not looking at the data, you will be strictly penalized with this kind of metrics.
Suppose that your system rejects all, but they all deserve to be rejected. So they are all true negatives and the system is perfect.
Exactly. So you would have a problem with that metric in that case. That degenerate case has a problem there. Exactly. And that's the point, that the problem is really complex. First, there are many filtering different situations in which you need different things from the system, and in which the concept of what is valuable changes. And so you have many different evaluation metrics that say different things.
Julio, 5 minutes.
Sorry?
5 minutes.
5 minutes, okay.
He's still on his first slide.
No, it's the last one.
At least I don't see anyone sleeping, so I go home happy. Well, let's go back to this slide. And so we said, no, I don't want to go to this stage yet. Yeah, formal constraints. We have just two formal constraints that any metric should satisfy. The first one is, if the system output is not like the gold standard, then it's not optimal. Okay? Quite intuitive. And the second one, don't look at the formulas, is the growing quality constraint, which says, if we have a misclassified item and we move it into the correct class, then the quality must go up. Again, you will probably agree that any good metric should satisfy this. Are they trivial? Let me put you an example. Think, okay, so the X are things that we want to discard. And these are the things we want to keep, all right? So this is like the gold standard. Think of a system that says that these three things are good, and these three things are not good, okay? It has made 3 mistakes here, okay? And here, it has made 2 mistakes, 2 more mistakes. Now think of this other system. This system says that this is good and all the rest is bad. So, 1 mistake here. These are 2 correct guesses. And this is exactly the same as for the other system. So, I think we all agree that with any metric, the system should be better than this one. It makes 2 correct guesses better than the other one, right? Now let's think in terms of precision and recall. Here, precision on the positive class is 0 because we didn't find the relevant information, any of the relevant items. And recall is 0 equally. Okay? What happens on the other side? Precision again is 0 because we returned 1 document that is not relevant. And recall is 0 because we didn't find any relevant information. So for precision and recall, these 2 systems are the same. So is that a big problem? Actually what happens is that we have a sample space. thinking in probabilistic terms, we don't have enough information. So we can solve it with the smoothing techniques. Okay, so if we use some small parameter in both sides of the division, then we will quickly see that this system is already worse than this one. So we can solve them with the smoothing techniques. It's not a completely heartbreaking problem, and we can make revised versions of metrics so that they satisfy the constraint. And now the lead. How methods differ? So we have seen this figure which says that they say very different things. Now what happens if we only keep non-informative systems in this graph and we remove all the rest? So
How can you get lost in just one slide?
you tell me. Maybe precisely because of that. Okay, that's what we get. This is the same figure, just with less elements. This is with all test cases. This is just with non-informative system outputs. And if you look at it, it's like you have the boundaries. So approximately you have the cases where systems disagree more. No? Yeah? So what, in a way, what metrics do and why they differ is because they do different things with non-informative outputs. And so what is the morale? What we can do about it? Yeah, I got completely lost. So looking at what metrics do with non-informative systems, we can find 3 mutually exclusive properties. And these are not actions. This is not something we force metrics to do. In fact, they are mutually exclusive, so they can only satisfy one of them. But these axioms model what metrics do with non-informative systems. And they induce metric families. So if there is an absolute gain for single document classifications, then we have a metric family. If all non-informative systems have the same quality, like mutual information, measures based on entropy, we have a different metric family. And when doing nothing is better than doing random, and think, so what can you do non-informatively with a span filter? You can remove everything, or you can just leave everything as positive. In the case of span filter, not removing anything is better than removing everything, because it gives you more work, but at least you don't lose the valuable information, right? So you can think of different scenarios that fit each of these properties. The telephone company could be in the first, the CIR reviewing problem would be the second, because non-informative systems, I do not care about them. I want them to have the same quality. And the third one could be the span filtering. And then we can classify all metrics into one of these 3 families. So here we don't have a single great metric that is good for all, and that's the one that you have to choose. The morale here is that you have to know exactly what you want in your problem, what is the right thing to do with non-informative systems, and from that you can derive a family of metrics that you can use. I guess I'm over time, no? Okay. You're going to miss a very fascinating end of the talk that you're going to have now. Presentation by Enrique follows directly from here and studies the retrieval problem, the one you're most interested in. So that's what you're going to have now. And that's it.